Good morning. Thanks for the invitation. I'm very happy to be here and tell you about our research on planetary materials. They are complex, naturally dirty, challenging to material simulations. We study rocks at high pressures and temperatures with variable composition. So from the start, you can see that these are high throughput calculations in phase space. And they are complex in the sense that you have oxygen, iron oxides in solid solutions with silicates. And so that's the level of complexity, all solid solutions. So the purpose of this research is to understand processes like this. As you see here, planetary interiors from which we only have indirect information. Earth is a dynamic, chemically differentiated system that has been evolving for 4.5 billion years. And the difference in temperature between the core and the surface drives heat flow that is carried mostly by convection in the mantle, very small temperature gradients. And decompression of hot rising material produces melts near the surface that solidify and form a crust. This melt leaves behind a solid that has different composition, and the average composition of this system, solid melt, has also different possibly different composition from the source region. So it's a complex, these are complex processes, but there has been a great deal of progress in understanding it. And this is what I'm going to try to show you today. So there is very little direct evidence from the Earth's interior. We see the crust, pieces of the solid left behind that sometimes is shoved to the surface or expelled in volcanic eruption. So these are the compositions that guide our research. But there is little direct sampling of the deep mantle. We rely on indirect information like this. This is the seismic velocity model, the preliminary reference model that's kind of old and is one-dimensional. It's one-dimensional. So this was produced from the seismic record of 100 years of information about earthquakes, travel times, and inversion of travel times gives this average velocities as a function of depth. So there are two major velocities as a function of depth, the compressive velocity, and you can see in the region of the mantle that I'm going to study, it's the lower mantle here. It's above 11 kilometers per second. And the shear velocity, about 6-7 kilometers per second. So this discontinuities here, this is depth, velocities, and density. These discontinuities are produced by phase transitions in mineral phases that we know very well. But the lower mantle, as you see, is kind of smooth, no major discontinuity there, and we try to understand the composition of the mantle, temperatures of the mantle by analyzing these velocities. Density is determined not by travel time, but frequency of oscillation modes of the Earth. Today, we have more information. Of course, there are lateral temperature variations caused by lateral velocity variations caused by lateral temperature variations, and seismic tomography is performed with the seismic waves. This is a shear velocity model. And there is a great deal of correlation between fast regions. This is the range of lateral temperature velocity variations, for example. This is fast regions, slow regions. They correlate well with cold regions or perhaps hot regions with different chemical compositions. So our work is to figure out, materials properties that that allow the interpretation of these tomographic models like this. Also, so these are the velocities. We assume that for this type of interpretation, we start that these are isotropic. At pointwise in the Earth, it's isotropic, and the velocities, compressive and shear waves, they related to the elastic moduli of the isotropic medium. That is book modulus K, shear modulus G. So this is the compressed velocity, shear velocity, and this is the bulk velocity that's easier to analyze. It's linearly dependent, but it's easier to analyze than P, the behavior of P. And of course, then we needed to do, we calculate these velocities, acoustic velocities in crystals, and then we do isotropic averages. And after that, we do polycrystalline averages in aggregates. These are standard techniques in mineral physics. Yes?
My question on the first slide. Can you use your microphone so that on the first slide where you showed, this trace, so in the inner and outer core, is it still solid, or is it?
Oh, no. This is the core, 2,900 kilometers depth, 6,300 here. This is liquid.
Okay.
Liquid iron is convecting here, and that is what generates the geodynamo.
Okay, but then the inner core is no
solid.
Longer liquid.
It's solid, right.
Okay.
So you have, again, shear waves propagating in the core, okay, in the inner core. So here, okay, so these are what we calculate. I told you we do calculations in crystals and elastic constant tensors as a function of pressure and temperature. Geodynamicists also use the proper thermodynamic properties we calculate. These are the most advanced fluid dynamic simulations of the Earth. They use density, book modulus, thermal expansivity, specific heat. Thermal conductivity is a very important property as well. But viscosity, subsolidus viscosity is still a great challenge to figure out. And geodynamicists, they can use fluids of more than one density with different properties and try to reproduce flows whose images can relate with seismic tomography. So this is an integrated field, totally integrated field today, thanks to a great part to mineral physics, because we provide these quantities, these velocities, velocity ratios to seismologists to interpret the Earth, and properties for geodynamicists to run fluid flows and try to interpret seismic tomographic data as well. So it's an integrated, simulation is the way to go here. Experiments are challenging. I will refer to pressures and temperatures next.
So may I ask a question? Just going back to your previous slide, the input that one would need for calculation is basically a chemical composition of pressure, let's say, or density, and perhaps a temperature.
Right.
So how are these things known, especially the chemical composition? Or does that have to be guessed?
For example, we know composition of crust, oceanic crust, continental crust. We know composition of the region right beneath the crust, because this mantle, part of the mantle gets shoved up to the surface, and we know the range of compositions that is seen. And there are, this is low pressures and temperatures, relatively low, so experiments can be done. So you pick so you can cook in a diamond anvil cell or in a high pressure cell samples with the real samples. And so we know the compositions in this region. We know compositions of magnesium, the light elements, we call light, but it's not really compared to hydrogen and helium. Silicon, oxygen, magnesium, the major element, earth-forming elements. We know solar compositions. And meteorites, primitive meteorites that form the Earth, we believe form the Earth, they have this major element ratios that are quite similar to the sun. So one of the, I'm not going to discuss this problem here, but the idea is that the Earth should also have these ratios, but it apparently not, and that's one of the major questions about the lower mantle. What is down there? Okay, but there are plenty of samples in different kinds of rocks that are and meteorites.
And how? I'm sorry to hold you up, but just
no, go ahead.
Just for my interest, I mean, I know that one can get information from what comes out, for example,
Yep.
from volcanoes or
Yep.
what's pushed up it.
Yep.
Also, and there's a certain amount of direct sampling where
Yep.
people drill holes. How
Right.
deep does that go? How far down?
12
can one see?
kilometers is the
Okay.
deepest
Okay.
in Russia. I don't remember exactly where in Russia, but nothing more than that. We have samples, diamonds, coming from about 410 kilometers depth. These are kimberlite pipes,
Right.
you know, explosive volcanoes in South Africa, for example.
Okay, thank you.
Yep. We see inclusions, diamond inclusions, not, you know, that's what comes from 410 kilometers. Okay, so this is the lower mantle. We have bridgemanite, magnesium silicate perovskite with iron, ferropericlase, MgO rock salt structure with iron, calcium silicate perovskite. It's a highly anharmonic phases. It's a small amount in the mantle. And so these are the main phases we are concerned with. Deep here, you have post-perovskite, a transition in bridgemanite. This is bridgemanite, and transitions to post-perovskite at the conditions of this region here. So we have 23 gigapascal, or 230 kilobars, and 135 GPa here at the core mantle boundary. 2,000 kilometers, 2,000 Kelvin, 1900 Kelvin here, about 4,000 Kelvin here. So this is the mantle. Velocities, as I showed before, compressive for up to 14 kilometers per second. Seismic waves are we like to analyze the fastest periods of 1 second. So that gives you an idea of the type of resolution seismic tomography can have, 10 kilometers. So 2000. So the iron concentration here is important. In ferropericlase, it's usually around 15, 17. There is a range that is observed. Here you have about less than 10% iron, but you have ferrous iron, ferric iron, and you have aluminum that produces ferric iron here as well. And this transforms to that phase that was discovered in 2004. So this is the range of thermodynamic conditions and composition. But because X is around, iron is around 0.1, that facilitates these calculations tremendously, okay? So I'm going to show you today, so spin transitions or spin state changes in iron under pressure in the mantle, the lower mantle phases, that's where the pressure temperature conditions exist. So these are the phases that I'm going to show. I'm going to focus greatly on ferropericlase. And I will tell you about the manifestation of the spin crossover in the mantle in seismic tomography that we believe that we caught it. If I had time, I would go beyond Earth and show you the new silicates that we discovered, but we are not going to have time for that. And verification of low pressure, the new phases, completely new phases, but have been confirmed experimentally on low pressure analogs. So the methodology that has been using most of what I am going to show is not new, but results are robust and they have useful accuracy. But where you see LDA, so I've used the FT plus U, LDA plus U, it gives the best, LDA gives some of the best structural properties, and better than LDA only scan, R2 scan, that meta-GGA kind. So where you read LDA, you might think today you would redo this with a meta-GGA. Density functional perturbation theory for DFT plus U, and some electron calculations for Moos-Bauer quadrupole splitting. Quasi-harmonic approximation is also not so new, is not new, but today you would use some quasi-particle phonon dispersion, temperature-dependent phonons for these calculations, and we have been using them. And so what is most crucial here was the semi-analytical method to calculate high temperature elasticity that we developed. So this is the quasi-harmonic approximation. It's simple and approximate. P, the derivative of the free energy as a function with volume. It's approximate, quite approximate. In principle, the thermal pressure is not really isotropic, but this is a decent and good approximation. So this is a quasi-harmonic approximation. Elasticity, the thermal elasticity in a crystal, solid solution or not, is obtained the following way. You have equilibrium structures versus volume, calculate phonons, do thermodynamics for the equilibrium structure, strain, again, relax the structure, redo the thermodynamics, and the elastic coefficient, isothermal elastic coefficients are the second derivative of the free energy with respect to strains. We needed the adiabatic elastic coefficients, and that there's another correction there. As you can see, the high throughput nature of this calculation that we start doing in the late 90s. Today, it has been facilitated greatly by semi-analytical expressions for this quantity here. Essentially, we need mode Gruneisen parameters, strain Gruneisen parameters in order to carry out these calculations more efficiently today. And that's possible.
So I'm sorry, may I ask for 2 points
Yep.
of clarification?
Yep.
So first, on the previous page, what was quasi about the quasi-harmonic approximation? I mean, that looks like just the F above looks like the harmonic fluctuation.
That's right. But the frequencies depend on volume, right? And that's why it's called quasi.
So at least conceptually, therefore, basically you get the phonon frequencies as a function of volume, and then put that in.
And that offers very decent results. And you can actually constrain the range of pressures and temperatures where this works well. It manifests failures of this approximation. They manifest very well in the thermal expansivity. Maybe I'll point out that later.
I see, but that means that if I want to, do I view this as a function of volume or pressure? In other words, presumably.
This is a function of volume that's optimized at static conditions, 0 Kelvin, no 0-point motion, right? Yeah. And then you have frequencies there. Of course, as I said, this is approximate. P comes, the pressure is derived from this expression, but the thermal pressure, the EDV, the vibrational free energy DV, is not isotropic.
Right, so that's
that's one of that comes out if you treat the problem at this level. Corrections can be included. It's not major.
And then on the next page, you refer to Gruneisen parameters, which are again that nonlinearity. So this is the point is that you need the volume dependence, or this, because this just looks
you need
linear.
the strain dependence of frequencies.
But your previous thing just said frequencies that depend on volume.
Correct.
But now you need more information.
Yes.
To get, okay.
Exactly. We use some tricks to get the omega d epsilon from the compression curve, from the compressed structure, because the compression is not isotropic. Tricks, okay? But they work very well. The method has been published, the code has been published, so and there are tests. So it was in 2003 and 2004 that the spin state change in ferropericlase and bridgemanite, the perovskite phase, were discovered. So you can see the type of claims that are done in these papers here towards lower mantle discontinuity. Data has not been confirmed, and possible non-convex layers in the deep mantle because of the possible change in optical properties across the spin transition. So this problem has not been addressed. So here is the spin state change. I'm sure you were familiar with it. So you have a 3d6 iron 2+ in octahedral field, and the crystal field splitting, a triplet and a doublet, 6 ions. This is the electronic configuration. And the crystal field splitting, Unruh energy splitting with increasing pressure. FeO bond length decreases, crystal field splitting increases, and you start having a transition. So here you have 5 electrons up and down, total S equal 2. This case, at higher pressures, S equal 1, and the ultimate pressure, S equal, you would get S equals 0, a very large crystal field splitting. This state here does not happen in the mantle or in the earth, but it happens at higher pressures. So this is the framework, and these are with the calculations we do are single configuration, single determinant calculations, and involves crystal structure relaxation and Taylor distortions to stabilize these states. So here is what happens.
Yeah. So why do you say that so the S equals 1 doesn't occur?
Not in the earth.
Okay, but the S equals 0 does?
Yes, that's what I'm going to show. I can show you later the total energy, the enthalpy of all this. There's more than one intermediate spin state S equal 1. And none of them have energy lower than the lowest spin state or the high spin state. Yeah.
So it's a computational statement.
It's more than computation. I'm going to show you an experiment. Okay. Okay. So Mohs-Bauer quadrupole splitting is Mohs-Bauer spectroscopy. Iron Mohs-Bauer spectroscopy is what's used to determine these spin states. Okay, experimentally. So here is when you replace magnesium by iron high spin, the octahedral expands non-isotropically because of the Taylor distortion, have minority electron will spin down. And when you replace with the low spin state, it contracts. So across the high spin to low spin state change, you have a contraction of octahedral, of the ferropericles octahedron by 8%. This is huge. This is huge. And this is what we started doing in 2004. The FT plus U was not even published. As we know today, it was not even published, but that was collaborating with co-author Stefano De Gironcoli. So here is, for example, 18.70% iron, 75% iron. It's 64 atoms per cell, and I have 6 iron ions. This is MgO, right? Six iron ions, and they are as far as possible from each other. This is the compression curve of the high spin state, low spin state, and superposed to the experimental compression curve for this composition. And as you can see, there is good agreement with the experiment, but you can see clearly that the crossover happens in a broad pressure range that it starts at about 45 and ends at about 60 GPa. It's not a sharp transition. It's a continuous crossover here. And this result, this picture here, so here's the compression curve when you have a supercell, and 1/3 of ions in the low spin state, etc. So this result inspired me to propose a model for this, this solid solution, MgO, FeO solid solution going across the spin transition. So there is a mixed spin state. There's some region, some pressure region where you have pressure range, where you have some ions, in my mind, in the low spin state and some ions in the high spin state. How do you deal with that? Well, you make a solid solution of 2 solid solutions. One is the high spin ferropericles and the other is the low spin ferropericles. And you have mole fractions or low spin fractions, N. And the first calculation showed that it was done with an ideal solid solution where the volume of the mixed spin region is the weighted average of the volumes of the N members, high spin and low spin, both N members with the same iron concentration. In this approximation, the free energy is given by this expression interpolated between those of the N members and a mixing free energy here that's ideal in this case. It's the old RT n log n plus 1 minus n log 1 minus n. So what we need here is to calculate the Gibbs free energy of the high spin state and low spin state, which is given by the Helmholtz plus, it's given by F, not Helmholtz, yeah, plus PV, and then iron magnesium mixing entropy that we say it's the same for both spin states. Here, this free energy here consists of the static plus vibration, that's the quasi-harmonic, but there is a magnetic entropy term that I have not, I have approximated also. It's given in the atomic limit. In other words, if you have an ion with ions with S, with spin S, and you have 2s+1 states per ion. So this is certainly something that is overestimated, and we can figure out this, we can see what the effect of some overestimation here. Better models for this spin entropy would be very, very welcome. And this mixing entropy here is just the ideal one. So we have analytical expressions for several of these terms, and what really is calculated by first principles is this quantity here, okay? And this PV term for each one of the phases. And if you minimize that free energy with respect to n, you get a simple expression like this: the population of low spin states, 1 plus this quantity here. M is the degeneracy of the minority electron orbital, 3, the 3 to 2G states. S is equal to, and here has the difference between static plus vibrational energy of the two end members, high spin and low spin. So this is the phase diagram, if you wish. The low spin fraction, 0 at low pressures, 1 at high pressures. This white line is if you don't include vibrational effects. This line here, black line, is if you include vibrational effects at the middle of the crossover. There is experimental data for 2 different concentrations, and you have to be careful because this phase diagram above, when X is above 0.2, it becomes dependent of the iron concentration. And so you have to be careful making this comparison, but there is very interesting results here. This 10% phase diagram, middle of the transitions right here. We underestimate in the first version of DFT plus U, we underestimated this transition pressure. Today we kind of overestimated a little bit. But the experimental phase diagram is a little different. Andy once asked me if the phonons across the spin transition, they are harmonic, what it is. In DFT plus U, they are. So this result here was inspired by our question. So we had one single iron in a 64 atom cell. So you can stabilize the high spin state, the low spin state throughout the entire pressure range of the mantle. This and calculate, phonons, and these phonons are unfolded into that of the primitive cell. The low spin state is stable. You don't see any unstable phonons at 0 GPa. The high spin state is stable at the bottom of the mantle. So it's as if you had 2 different states, stable, and the transition is sort of a first order transition in which you have a large volume change, but you have 2 minima in parameter space of the free energy, the total energy surface in parameter space. So in DFT plus U, you don't have phonon stability. That doesn't mean it is not there.
So I'm sorry, may I ask again, can you go back one? So first, on these figures, what are the sort of lighter colored things that look sort of like
these are phonons in a supercell,
right?
And then you unfold them into the primitive Brillouin zone of MgO, the rock salt structure.
I see, and this is just a representation of how the
That's right.
Works.
Yeah.
Okay.
Right.
And more seriously, 2 questions. One is, how sensitive is this to the value of U? I mean, this is DFT plus U. Right?
Yeah.
So where does the U come from? And how much
Yeah. U is calculated by linear responses.
Okay.
That's where it comes from. The interesting thing is, vibrational frequencies, they don't depend so much on U, or even on, they depend on the functional, but that's a second order effect on the free energy itself. They affect the transition pressure, for sure. You can move the transition pressure back and forth because that's at the point where the enthalpy difference is zero. So that's sensitive.
Right, you
And
must affect the high spin, low spin transition. I mean, here the
pressure,
frequencies are
pressure, not
yeah.
so much the structural properties, but the pressure, yeah.
Right.
So
there's only one iron out of 64 or whatever.
Yeah.
So
This was, yeah. Right, right. So yes, we did calculations in 6% iron where we had iron far apart and next to each other. The conclusion does not change. That's all I can say.
And also conceptually, I mean, the answer may just be that it's dilute.
Yes, exactly. Yes.
But the theory you presented previously was essentially the generalization to this richer situation of the usual binary alloy.
Yeah.
Thing. Now, I might imagine that somewhere in this I have a first order phase transition with phase separation. The binary alloy thing doesn't give me that. So where does phase separation around the first order transition?
You may have that. If you are x equal 0.5, you may separate. You may have phase separation.
I see. But it's the small x's here.
In two different ferropericles with different composition.
Yeah. Okay.
Yeah. This is very low. We were lucky that this is very low concentration. Okay. So this is the other experiment at 25% iron. It's interesting, very interesting. For example, you see the slope is nearly zero, and the slope here is mainly determined by the magnetic entropy, which is very approximate in my case. And also there is this issue here. You have 100% high spin at 90 GPa, not in my case. You're still growing through the rainbow here. And this has to do whether the high spin state can be stabilized at high pressures or not. Scan that does not stabilize that. So there is room for exploration of better functionals in this region here. And this goes away. This state goes away. You can see it going away. It's accompanied by anharmonicity and possibly multi-configuration states. So there is. So
sorry.
Yeah.
So this is kind of like binary, right? Like if it's low spin or high spin, what like as Saya's question, what about the intermediate? Like where would they?
It's very high energy. Can you wait for me? I'll show the enthalpy of those states. They are out of the map. Okay. It has to do with the octahedral coordination. It doesn't favor that kind of configuration. In super Earth mantles, they will come up, but that's a different kind of crystal structure. But there is another effect that we didn't include, and that's the fact that we treated the high spin, low spin as an ideal solid solution. It is not. You can do a full, can do a calculation of the excess free energy, how the energy changes when you change high spin, low spin configurations for the same low spin fraction. There is an effect. It's a small energy difference between different configurations, but when you're talking about the delta H is equal 0, any small change is significant. So you can broaden this this mixed spin region by going beyond ideal solid solutions. So effects on the structural properties are pretty simple. So this is the experimental compression curve. This is the first DFT plus U that was approximate ideal, doesn't give the right transition pressure. But here you go, the compression curve at 300 Kelvin. And at the higher temperatures, this anomaly here in the compression curve increases with pressure and broadens as you increase the temperature because of the nature of the rainbow, right? So the book modulus, when you, in the mixed spin region, the compressibility increases anomalously, and the book modulus decreases. So you have these anomalies at different temperatures. And the book velocity square root of book modulus divided by rho also has this anomaly. So you can see right away that seismic tomographic images will be affected by the presence of ferropericles in the mantle undergoing spin transitions. Density is very well reproduced in the mantle. There are anomalies in thermodynamic properties. Yeah.
Can you say again what those dips are?
This, okay, so you have the compression curve, right? Okay, high spin, low spin, and this is the mixed spin region, okay? Compressibility is the VDP. It increases. So book modulus 1 over that decreases. Oh, decreases.
So that's measuring on the extent to which you have a discontinuity.
Yeah, right. This is very narrow in our calculations because we didn't have the non-ideality here. When you bring non-ideality, this broadens. And there was a different, and the transition pressure was wrong in the first calculations. It shifted, but, and with more recent calculations, it's higher. I'll show you, I'll tell more about that. So here you have anomalies in all thermodynamic properties. For example, at 50 GPa, you start in the low spin phase, increase temperature, go through the rainbow, you have these anomalies in thermal expansion coefficients. For example, at 0 GPa, you can see here that the calculated thermal expansivity deviates from experiments at this point, and that's when we identify the limit of validity of the quasi-harmonic approximation. This is 0 GPa, no spin transition. 50 GPa and above, we start having. So all thermodynamics properties have spin transition. In particular, this is the important one, the book modulus. You sit at a certain pressure, constant pressure, and temperature varies laterally. What happens with the velocity when the temperature varies laterally? This is a very important plot for the matter. So it was difficult to determine experimentally these elastic coefficients as a function of pressure and temperature and composition, but there are, between 2008 and 11, there were 3 different measurements. So cubic structure, 3 elastic coefficients, 1, 1, 1, 2, 4, 4. The first experiment, 3 different techniques said that there were similar anomalies in all the elastic coefficients. Brillouin scattering detected anomalies in C11, C12, but not in the shear elastic coefficient. In elastic X-ray scattering, the term said no, C44 and C11 have anomalies, but not C11. So at that point, we had, of course, we were studying this even before these measurements, but so this is the volume of the solid solution, right? It's the ideal solid solution. The compressibility, the VDP, is this, V over the book modulus, it also interpolates linearly between that of those of the N members, but has an anomaly term here that comes from the NDP, right? The low spin fraction varies with pressure. You can derive similar expressions for the components of the compliance tensor, which is the inverse elastic tensor. Also, the components interpolate linearly between those of the N members and has an anomaly term here, but there is a prefactor here that depends on the kind of strains involved in that particular coefficient. If the strain does not change volume in first order, which would change N, then you don't have this term here. Epsilon 4, a shear strain, does not change the volume of the structure in first order. Therefore, for alpha, S44 or C44, this term is 0. So we agree, this simple analysis shows why Brillouin scattering was the technique that was getting these elastic coefficients right. So how well are these coefficients? How good are these coefficients? 300 Kelvin, 0 GPa. We had calculations at 0 and 18.75, and these are measurements of these elastic coefficients of function of concentration. And you can see it's quite linear. So what we do is we do elastic constant calculations of the elastic coefficients at these 2 compositions and then interpolate linearly within this concentration range. Essentially, that's what we have been doing. Book modulus, shear modulus. Without spin state change, this is pretty good.
So which spin state are we in here?
0 GPa is the high spin state.
Okay.
Yep, this is 0 GPa, 300 Kelvin. Okay. So here is the book modulus and the shear modulus. So you did calculations of all the elastic tensor, isotropic averages, book modulus, shear modulus, And this is our prediction for 10 and 6% to compare with the experiments. These are the 3 different experiments that give very different values for the book models. Shear models are more closely related and doesn't depend so much on whether there is a spin transition or not. So we have some agreement with the experiment here because, of course, in order to analyze the mantle, you need to have as much agreement as you need, right? So we just did shift the enthalpy, the static enthalpy, by a value of 0.2 electron volts per iron in order to get the right transition pressure. That's all that was done in this calculation to get this level of agreement with the experiment. So this is VP, the shear velocity, and the book velocity that we like to analyze these 2 velocities here. So there is decent agreement as a function of pressure at 300 Kelvin as well, if we do this shift of 0.2 eV per iron in the high spin state.
Can you get that shift by changing U?
Yes, you get more than that. You don't get the right one. You know, if you do, of course you can change it, but you don't want to change by hand, right? You want to do different, you want to do, maybe use different functionals, scan, PBE, that's it, but you want to keep calculating you the same way. You don't want free parameter. You don't want free parameter.
If you were to tune you would
yes.
be able to.
Yes.
Okay.
So this is the major phase, 75 volume % at least in the mantle. Iron 2+ here, ferric iron coupled substitution or coupled with aluminum on this side here. This is very interesting. If you allow me, I will go through very quickly through what happens here. What happens in ferric iron in the silicon site is very similar to what happens in ferropericlase. And here, this is iron 3+, so 5/2, spin 5/2. Nothing happens with this ion here, no spin state change there. And there is no spin state change in here. What is happening here is it's interesting. So I want to go through that. So as I said, Mossbauer, iron Mossbauer spectroscopy is what's used. At 0 GPa, the high spin state in the perovskite phase has a Mossbauer quadrupole splitting of 2.4 millimeters per second. At 30 GPa, you start seeing a different kind of iron that starts showing up with a quadrupole splitting 3.45 millimeters per second. And at 60 GPa, this kind of iron takes over. You can see clearly in the Mossbauer spectroscopy, there are different kinds of iron with different quadrupole splittings coexisting at the same time, which is the sort of picture that we have here in mind. So at beyond 60 GPa, there is only one kind of iron. So here is the Mossbauer data, just to show you how this looks like. I hope I don't have to explain this to you, but this is, it's absorption spectroscopy going through the sample of a gamma ray of this energy here that's produced by decay of iron. And then it's, if you have BCC iron, if you have BCC iron in your sample, you will absorb in the same energy. But if you have a different chemical environment, there is a quadrupole splitting of nuclear energy levels, and you have to shift the sample back and forth to adjust the frequency of this gamma ray by Doppler effect. So the quadrupole splitting of the absorption peaks, they are reported in terms of the splitting in terms of millimeters per second, the velocity of the sample. So at low pressures, you have iron 0 and a BCC iron and the low quadrupole splitting. And as increased pressure, you start seeing another two sets of peaks. That is the second kind of iron that is going up. So this was speculated to be the intermediate spin state. Why? Because the quadrupole splitting is larger. The electric field gradient on the nuclear side must be larger, and that cannot be produced by the low spin state, which is a more symmetric electronic density configuration around in the ion side. So this was proposed to be the intermediate spin state. Our calculations did not agree with that. So we looked for different kinds of iron, high spin, low spin. And what we did was just displace the iron 2+, and optimize the structure. And we found two kinds of high spin states, one with quadruple splitting 2.3 and one 3.3, and one low spin state with quadruple splitting much smaller, 0.8. In terms of energy, these are the competitive states. These others here are not. So what's the difference between these two states? It's the y coordinate of the iron. And as you can see here, this is the energy. It's a constant. This is 0 GPa, 30, 60, and 90 GPa. Of the two states we found, at zero pressure, you find this state. This is the charge density of the minority electron. So it's a YZ kind of T2G orbital that's occupied. And there is this other state here displaced along the y-axis that is the XY orbital that's occupied. So there is a change in electronic, the orbital occupancy as a function of pressure in the T2G manifold of the minority electron as you increase pressure. So this is it. Okay.
So you're saying, therefore, it's an orbital crossover and not a spin crossover.
Right. Yeah. And it's the same spin state. It's high spin.
By pressure?
Pressure.
I mean, the environment looked relatively isotropic. So what is it that tells
It's an orthorhombic structure.
Okay.
Yeah. And the compressibility of the axis differs.
Okay.
And that's it. Okay, I have to make a very long story short. If you put aluminum in the structure, aluminum enters here on this side to produce ferric iron. And there's in this site, there is no spin state change. So the fact that we have aluminum in bridgemanite and some ferric iron in this state makes life easier. We don't have to worry about high spin, low spin transition in the major phase. It's just ferropericlase that is the major one. So I'm gonna go quickly here, 5 minutes. Okay, so what happens in ferropericlase, book modules, shear modules as a function of temperature, if you sit at 75 GPa in the mantle, 75 is here, it's 1,500 kilometers depth. The pressure temperature range there is 2,000 to 4,000 Kelvin, just to remind you. So as a function of temperature, if you're sitting there at 75 GPa and the temperature changes, because you have flow, hot regions rising, cold regions sinking. This is what happens to the book modules. And of course, it depends on the amount of iron that you have in the sample, 12 or 21% here. Shear modules, the shear elastic coefficients always decrease with increasing temperature at constant pressure. But in this case here, you have this anomaly that end up increasing the temperature with increasing the book modules with temperature because of the spin state change. So you're here and you go through the rainbow and you see these anomalies. So you are there. So the shear modules decrease with temperature and the book modules increases with temperature. So the shear velocity has normal behavior. It decreases with increasing temperature. But the compressive velocity starts to get a little confused here because the shear modulus decreases with temperature and the book modulus increases. So the sensitivity of VP with respect to lateral temperature variations decreases because of this effect. So here, but of course, we don't have ferropericlase in the mantle. We have what we believe to be pyrrolite composition, 78 volume% of bridgemanite, 7% calcium silicate, 15% ferropericlase. Or you can vary a little bit the composition. You can see that the book modules of this aggregate is called pyrrolite, is a hypothetical rock composition that has never been seen on surface, but that's supposed to be the source region of what we see on the surface. So you have this anomaly here. So to make a long story short, what the signature should be, if you have a plume coming from the core mantle boundary, a high temperature conduit, a low velocity conduit in the shear velocity tomographic image, it happens that the compression of the compressive velocity, the sensitivity of the compressive velocity with lateral temperature variations decreases because the shear and book modules go in different directions. So this is what prediction, but in fact was more of a post-diction because there were, so these are, there were tomographic model. You have to look for these images in P models. You will see the signature of the spin transition in P models or relationship between P and S models. These are hotspots in the Earth. These are presumably volcanoes that come from very deep in the mantle, and they show up in the middle of plates like Hawaii. So these are some intriguing images, old images that we're seeing of Hawaii and Iceland. It's a single model of global model of P model. So you can see, so the interpretation, and this is not, there are others too, very intriguing. So the interpretation of these images were two, or convection is impeded in the middle of the mantle. The plume doesn't go through, it gets stuck here for some time, perhaps, or the P wave seismic are not sampling this region properly. And that was the interpretation. Nobody suspected that the spin transition could have anything to do with this. Similarly, cold plates sinking to the mantle have a similar anomaly, because it doesn't matter if the temperature increases or decreases, the anticorrelation between VS and BP, Book and shear models is similar. So you have this anomalies, this image here. So here, also, I can tell you there are other tomographic models that show the same. I'm going to skip this. This is how different rocks, if you have in a homogeneous mantle and it's with spherically symmetric velocities, you would see a bold here, a softening of the book modulus in the mantle. We don't see that, but this is the range of elastic properties that we get from different kinds of rocks. So what we did was analyze four S models and 4 P models. I worked with seismologists and geodynamicists to do this, and this was published in 2021. These tomographic models, they don't agree with each other. They differ from each other. Their images differ in many respects. If you sit at a certain depth and you calculate the velocity distribution at that depth, these models have different distributions centered around different points because they have different reference states as well. So the first thing is how to extract the robust common fit tomographic in these tomographic images, S and P models. So the first thing was to normalize these distributions and align them, and then ask the questions, how many, this is what we call the volt maps, point-wise in the Earth, or at each depth, how many models, point-wise, how many models agree on velocity changes by +1 sigma or -1 sigma, point-wise in the Earth. And this is what is called the volt maps. The volt maps here, for example, are cross-section in the Earth, under Asia, under North America. These are plates that start subducting a long time ago, and they are down in the mantle. The shear wave tomographic volt map, these are not tomographic maps. These are volt maps. They relate with tomographic maps. The darker the region, the greater the agreement, and the greater the velocity heterogeneity. The P wave models, you see the image fades. And this has to do with the smaller heterogeneities or disagreement between the maps. If the velocity heterogeneities are very small, the models disagree more. So, but this is consistent with the kind of expectation we have as an effect of the spin transition. And this is not one model, these are 4 S models and 4 P models. And this is a hot region in the mantle, the large low shear velocity provinces. Summary. Okay, so this is how we see the signature of the spin state change in the mantle. The iron spin crossover is not obvious global feature in the mantle because the mantle is heterogeneous. It can be observed in slab regions and faster and slower regions because the signature is in the velocity dependence of temperatures. And all these observations require high resolution tomographic images. Now we are zooming in into different regions of the mantle and analyzing these heterogeneities in S and P where we know, I think we know better the compositions of those regions. So I'm going to end here. And I need to thank my co-authors, postdocs, research scientists, and senior collaborators that have helped me to navigate this research, and students. Thank you so much. Oh.
So thank you for a informative and perfectly timed talk. So we had some questions during, but more questions? So if I may start just as a summary for a non-geophysicist.
Yep.
Let's say condensed matter physics and electronic structure impacts geophysics, as far as I can tell, essentially via the equation of state of these various compounds. And there are two levels of uncertainty in writing equations of state. Or the first one, which you sort of touched on at the beginning, is just what materials you have, right? You did calculations for some specific materials. And I confess it's still amazing to me that they actually know 4,000 kilometers below the Earth's surface what the materials act, or 2,000 what the materials actually are.
We believe, we have ideas. I mean, there are many hypotheses.
And then once one has a material, then there is a question of getting the equation of state of that material, particularly when it involves transition metals, which have both spin and orbital transitions.
Right.
And indeed, one of the things I learned here was that in addition to spin transitions, orbital transitions can be relevant in at least some cases. Okay, so then, so I guess that my general question is, in your view, are the current electronic structure methods adequate for the task, with the big uncertainties being essentially the context in which they're applied? Which materials do we have? How do we interpret these sound velocity experiments, which are averages over regions of unknown temperature and pressure? And which are the places where, in your view, let's say, better electronic structure is needed?
Right. First of all, there's great deal of uncertainty of what's down there.
Yeah.
And analysis has to be done also on statistically. If you're going to figure out what's the probability of these compositions versus depths, or in different regions, it has to be statistical. I think we have useful accuracy. What we care a lot, as you saw, the analysis of the effect of spin transition in the metal, whether it's seen in tomographic models or not, is qualitative. So we care about trends, gradients with temperature, gradients with composition, properties with respect to composition, not necessarily the absolute values, but the relative values. Heterogeneities are giving us delta V over V, percentage-wise. So the equations of state might not be super accurate, but you get trends and that are quite good. So absolute values are less important. Gradients are also very important. There is, we don't know the composition of the mermaid.
Right.
You know, the magnesium ferropericlase should be less abundant in the deep mantle if the Earth's composition, the element ratios are similar to that in the sun, and we would expect that that is the case. And why not is another big question as well. But there is room for improvement, of course. Scan is the biggest improvement that we've had so far. The agreement with the experiments are much better. When you start going to the core, then there are other kinds of questions. But in the mantle scan, these are non-metallic systems.
Right.
So that's scan or scan plus U. Some people say scan still needs a U, but a smaller U. I think this is to be investigated. This is one of the questions that I would investigate for what is needed to get the transition pressure right? And also, you know, it's high temperature, vibrations are there. Are they harmonic or unharmonic? I think we can handle unharmonic states these days. So we can calculate free energies with unharmonic phonos as well. But I think the main question is, getting the spin transition more accurately as a function of pressure would be.
So then, as you said, the outer core, which is basically metallic iron, if I understand correctly, that presents a whole separate set of problems.
Oh, the core is a very different set of questions. But, you know, that's for Earth. If you're studying Mars, you know, it's different. Lower iron at low pressures, even the high pressure form of iron, HCP iron, you can't reproduce. I haven't seen a functional that reproduces the equation of state at low pressures. Above 100 GPa, PBE gets right. But below, you have antiferromagnetic, I think, fluctuations in HCP iron. That's what I read. I don't understand that, and that does, not to mention, if there is magnetism, you have magnons. We have not introduced magnons in this calculation, but that's iron.
Right. Okay, and then if I come back to the region of the mantle where one is dealing, as I understand it, the theoretical problem is materials which are insulating with the relatively large gap, and in which the troublesome species, which is iron, is relatively dilute.
Yes. But nevertheless, changing spins. First of all, without iron, the gap is about 10 electron volts.
Right.
With iron, it depends on the configuration. Low spin is 3 electron volts approximately. High spin, it's about 1 electron volt. Intermediate spin, there's more than one configuration. You have, you know, from 0.5 to 2 electron volts. And that's why the title of that paper in Science in 2004 was Non-Convective Layers in the Lower Mantle. Across the high spin to low spin state change, the gap opens from 1 to 3. That means infrared can go through, light can go through, radiation, conduction through radiation is more important, and that damps the vigor of the convection in the door. So that is the implication. So this is an important problem too, figuring out what happens with the optical properties across the spectrum. That's cool problem, very cool problem.
And that's, if I go back to the picture that iron is a dilute species,
Yeah.
then the iron states are like defect states living inside this approximately 10 eV or
Right.
whatever is gap.
Right.
And if I understand correctly, then what you're saying is that understanding the position of those iron states relative to the band edge,
Yeah.
which is what you need for,
Right.
that's what you mean by this 1 EV
Yep.
or 3 EV gap becomes important.
This is the gap in the T2G manifold, the crystal field gap.
That's just an iron to iron transition.
That's right.
It's not,
Exactly. That's right. That's right. The optical properties, my picture is very simple here. I'm telling you the gap in the 1 electron,
right.
you know, picture.
I see. So these are still iron to iron transitions. Okay, my last question, I'm sorry to hold everybody up, is just particularly as one gets away from totally dilute iron, if one gets to 25% or 15% or something. Right now, I understand the different spin states and different orbital states have different local octahedral or whatever you call it volumes.
Yeah.
And that because there is, the orbitals are involved, there is an anisotropic kind of Young-Teller thing. So that suggests that the different states may be coupled by a strain, which can propagate over longer distances.
That's right.
Right. So is that coupling?
That is the non-ideality that I mentioned. When you take into account the difference in energy by changing the configuration, it's the same high spin, low spin fraction, but you change the spin configuration for irons. So that's, I would describe this phenomenon as a deviation from ideal solid solution. That, high throughput calculations in configuration, atomic configuration space, that's what it is.
I wonder if there's also just interactions.
There is, independent
irons.
Right. Exchange, coupling,
Yeah.
second neighbors, right? Yeah, that's what I think it is behind this picture. No magnetic entropy. I mean, low, very low magnetic entropy. Magnetic entropy gives the inclination here. This is very low magnetic entropy. More, accurate models for this spin magnetic entropy are important. And also here is a problem of which functional you're going to use. Which functional gets rid of the stable high spin state at high pressure. So, yeah. But this is 25%. Yeah.
Yes, I see. So other questions?
Maybe I got one quick one. So is there also an issue of pseudopotentials if you go to high pressures?
Well, if you have iron subjected to above 100 GPa, you need the iron 2+, right? You need no, you need the 16 electron pseudopotential. It's not major, but we're not trying to get melting temperatures of iron here at above 150 GPa. It's still lower mantle, lower than 135 GPa. It doesn't make much difference, but yes, that's at higher pressures. Yes, you have to care about that, and it makes a difference. It affects the melting temperature considerably, 800 Kelvin, deep in the core. Yeah.
Right. So let's thank Renata again for
Thank
very
you.
stimulating.